Hasn't been recording and it hasn't even been printing. And so I had trouble printing the bonus quiz this morning, so the morning class I just postponed it to Monday. But I finally got it to print though. Ionic compounds, when we do a Lewis structure for these, they're going to look different. So for example, sodium chloride. We'd have something like that, etc. We did the examples last time. But when we deal with covalent compounds, we have two types of covalent compounds that we look at. The first type would be lattice. Covalent lattice compounds. So if we look at the Lewis symbol for carbon, carbon has 4 valence electrons. When we write the 4 valence electrons like this, carbon likes to form 4 single bonds, or 1 double bond, 2 single bonds, or 2 double bonds, or 1 triple bond, 1 single bond, some kind of combination where we use all bonding electrons here. And the case where we form 4 single bonds, it'll form a tetrahedral carbon like this, and we end up forming a tetrahedral carbon network where each of the carbon atoms is tetrahedrally bonded to the other. So when we look at this, I mean, where does this end? It doesn't really end, it just keeps going. And so this is what we'd call, let's say, a network. Covalent lattice. And eventually it's going to stop. You know, it'll stop at the end of the crystal. Do you know what this is? Diamond. And when it stops at the end of the crystal, then we have these electrons that are what we call dangling. These are called dangling bonds or radicals. And so the surface is dangling bonds here. And the surface atoms aren't as stable as what we call the bulk or the interior atoms. That's always the case. Surface atoms are always less stable than interior or bulk atoms. We can see this in the sugar cube. When we take a sugar cube and dissolve it in water, does the cube just shrink down? Does the cube just get smaller and smaller, so eventually we end up with a mini cube, or what happens to the sugar cube when it dissolves? I don't know if you've watched it, but when you watch a sugar cube dissolve, you know what atoms or molecules get dissolved first? The ones on the face of the cube, the ones on the edge of the cube, or the ones on the corner of the cubes get dissolved first? The ones on the corner, because the ones on the corner are the most dangling, you know, they're of the least things that are bonded to it. And then the edges. So eventually this, you know, when it dissolves, everything just rounds off. You know, the corners round off, the edges round off. It becomes a rounded blob. Well, you know, that's because these surface atoms are more reactive. And so what do we do with the surface atoms? Well, nothing. So when you're drawing this, you know, how big do you draw this lattice? Well, you could draw it as big or as small as you want, because we could have diamond crystals that are tiny or diamond crystals that are very large. You know, it doesn't really have an end. You know, people will try to make bigger and bigger diamonds, or find bigger and bigger diamonds. So that's a covalent lattice. Carbon can also form double and single bonds. So we can form 1 double, 2 singles. If we do something like this, then we'll generate this lattice. This lattice just extends, except this is a 3-dimensional lattice. This is a 2-dimensional lattice because these hexagonal rings of carbon atoms are trigonal planar. In other words, they're flat. something like this, etc. So this is diamond, this is graphite. We have quartz. Quartz I talked about before. These are going to be tetrahedral silicon atoms bonded to what we call bent bridging oxygen atoms here. So we've got a silicon. Quartz is just going to extend on in 3 dimensions. This is SiO2 quartz. And we'll just stop it. And so they're going to be dangling, let's say oxygens are going to be left dangling, or silicons are going to be left dangling when we stop the crystal. One thing that like diamond, graphite, quartz have in common is extremely high melting points. And these are fairly hard materials. Although graphite doesn't seem very hard. I mean, graphite's used in pencil lead. So. But if you've ever tried to melt pencil lead, it's very difficult to melt.
Are we all going to take the quiz at the same time? Or do we, like, what's the...
I'm sorry?
Are we all going to take the quiz at the same time? Like, how do we...
Yeah, all at the same time.
I see.
Yeah, this will be the easiest. It's a little bit long, so I'll give you... extra time. So, yeah, if you're prepared for it, best to get it over with. It's bonus. I mean, these are free points. It's like, the worst you can do is 0 points, but you're not losing any points. Too much risk. So covalent compounds, we have lattice like this. And then the other type of covalent compound we have are molecules. We spend most of our time looking at molecules. So much so that when I ask people to draw the Lewis structure for an ionic compound, they always make it molecular. And so I'll ask somebody to draw the Lewis structure for sodium chloride, and they come up with something like this. That's not how we draw the Lewis structure for an ionic compound. That's how we draw the Lewis structure for a molecular compound. For molecular compounds, we show the bond as a line or 2 dots. For ionic compounds, the ionic bond is just the attraction between the positive and the negative. Here. Sometimes, I'll ask somebody to draw. Actually, I don't really ask anybody to draw quartz. It's too hard. Or diamond. But a lot of people think SiO2. When I ask about the Lewis structure, they'll say, "Oh, SiO2 is like CO2." No, SiO2 is not like CO2. CO2 is a gas. SiO2 is a very hard material. SiO2, quartz melts at over 1,000 degrees Celsius. CO2 melts at an extremely low temperature, well below room temperature. So this is not right either. And so these things get mixed up. Fortunately, there aren't too many network covalents that we worry about. That's pretty much it. Network covalent elements and network covalent compound there. And so most of the time, if you guess molecule, you'd be correct. So, the tricky thing this is ionic here, not molecular. So the tricky thing sometimes is to deal with the chart. So let's do with iron and oxygen. Iron and oxygen, is that going to make a molecular compound or is it going to make an ionic compound? Yeah, I would expect this to make an ionic compound. But there's one problem, and that is iron. You know, iron, how many valence electrons does iron have? If I wanted to draw the Lewis symbol for iron. Eight? How many valence electrons does iron have? Iron, what's the electron configuration? That's argon, 4s2, 3d6. So it has 6 valence electrons, is that correct? Iron? 8 valence electrons? 2 valence electrons? How many valence electrons does iron have? Well, oxygen's easy. Let's go with oxygen. Oxygen, do you know how many valence electrons oxygen has? Oxygen has 6 valence electrons. It's 2s2, 2p4. So that's where I got it. And we don't differentiate which of these electrons came from the 2s, which electrons came from the 2p. But we know it's going to be helium, 2s2, 2p4. We've got iron is going to be argon, 4s, 3d, 4s2, 3d, 6. So what do we do with the dots? What we do with the dots is it's complicated for transition metals, right? Because transition metals have how many valence electrons? In other words, are the 3d6 valence or the 4s2 valence? Which are outermost? 4s or 3d? So it has 2 valence electrons. So iron has 2 valence electrons, so we do that. But the problem with like the transition elements, is that sometimes the inner electrons can react. Like the D, this is not a filled D. And not only that, we have a paired electron here, making it more reactive versus the unpaired electrons here. So it's easier to ionize this paired one than these ones over here. And so iron will have the 4s. These are going to be the valence here, the 4s. But we also have 6d electrons that are inside here. One of them is going to be quite a bit more reactive. The others are less reactive. 1, 2, 3, 4, 5, 6. And so these are the 3d. And so we have a choice here. If we're going to come up with a Lewis structure, we can make iron 2 oxide. That is, oxygen plugs off both of these. And then the way we show that is we don't show the inner 3d electrons. We just show like this. It's lost the s electrons there. This is going to be 2 plus. Yeah. And then oxygen's going to gain those. And it's going to have an octet. And so this is iron 2 oxide, FeO. This is what we'll call a molecule of iron 2 oxide, or a formula unit of iron 2 oxide. Formula unit. If we look at it, you just build up the crystal lattice just by adding more and more ions. Which is bigger, oxide or iron 2? Oxide? Yeah, oxide is bigger. anions are usually bigger than cations. So this would be oxide, this would be iron 2. And then we just build up a lattice, this, etc. We could also form iron 3 oxide. Iron 3 oxide is going to take this one D electron here and both the S electrons. However, we're going to still write it the same. It's going to be like this. We're going to not show the D electrons here. This would be iron 3 plus. Oxide. So it's going to give up 3. Oxide only wants 2. So we'll need another oxide here to take an additional electron. But this one wants one more electron, so we'll need another iron. We'll just throw an iron down here. But this iron wants to give up 3, so this one gives 1 here, but we'll need another oxide to take the other 2. And so we form Fe2O3, iron 3 oxide here. This would be one formula unit. It doesn't matter how you range them. We just need 3 oxides and 2 irons. And then we'll build up a lattice. Iron 3 is going to be a bit smaller than iron 2 because of its higher charge. Oxide will be the same size. So for transition metals, it gets messy. And therefore, we really, when you look at transition metals and Lewis structures, they often just ignore the electrons around there. You know, that's unlike something like aluminum. Aluminum is very easy because there's only one charge for aluminum, and that's aluminum losing its 3 valence electrons. Aluminum has an S and 2 S's and 1 P electron, shown like that. So aluminum's quite easy. But the transition metals are messy, and so those don't usually appear nice Lewis structures like this. So that's about as complicated as things get here. For molecules, they can get quite complicated. So what we do is there's just a set procedure that we use for drawing Lewis structures for molecular compounds. So we'll just review those steps. Step 1 is to sum the valence electrons. So transition metals typically don't occur in covalent molecules. They can in Chem 1b, but in Chem 1b we'll just kind of draw them without anything around them. So we sum up the valence electrons and adjust for charge. So if we have a +1 charge, then that means we have to lose 1 electron. If we have a -1 charge, that means we have an extra electron for each negative. 2, we build a skeleton structure. A skeleton structure, all that means is that we attach everything together, all the atoms with a bond, a single bond. You know, a single bond would just be a line. When we build the skeleton structure, we want to note a couple of rules that help in determining the structure. Usually we place the least electronegative atom in the center. So place least electronegative, En for electronegative, element in center. It's a rule. And so sometimes the rules are broken. can be broken like here. Like, what's more electronegative, hydrogen or oxygen? Oxygen. But oxygen goes in the center of water. So we add another rule to help us with this issue here. So this is a violation. But it's not a law. So violation of the rules is not that big of a deal. The other rule that we add on top of this is that hydrogen and fluorine form terminal atoms with single bonds. Only. We have, like, when we have a center atom, we often call that a bridging. Like, for example, this oxygen here is a bridging oxygen. It forms a bridge here. These hydrogens are terminal.
What is a terminal atom?
The terminal atom does not bridge with another atom, and so it just ends. So this would be a terminal atom. An example of a bridging atom would be something like this, where this carbon bridges between atom A and atom B, but atom A terminates with hydrogen here. And so that's the difference between terminal and bridging. All right, 3, we're going to complete the octets to the most electronegative elements first. So 3, complete the octets to the most electronegative elements first. For extra electrons go on central or bridging atoms. Five, if there are not enough electrons to complete the octet, then try double or triple bonding atoms. Six, determine if any resonance forms exist if so, draw all possible resonance forms connecting them with a double-headed arrow. Double-headed arrows are reserved for resonance forms. So let's say I have a resonance form here on the left, I'll connect it to a resonance form here on the right using a double-headed arrow, and just keep connecting them, double-headed arrows, depending on how many resonance forms I have. Seven, draw the resonance hybrid. If necessary.
What is necessary?
What is necessary? If I ask you to draw the resonance hybrid on the exam. Otherwise, we usually don't draw it. Don't draw it because it's more complicated. And so this is usually like a bonus question. You know, if you look at my past exam, I throw it in as a bonus. Meaning you don't have to. Eight. You know, when we have the resonance hybrid, it's a little harder to analyze. We usually analyze the resonance forms, or if there are no resonance forms, we just analyze the Lewis structure. But we're going to analyze the resonance forms, or the Lewis structure, or Lewis structure. If we analyze the resonance form, we usually just analyze only one, not every single one. For electron geometry, EG. EG is electron geometry or electron pair geometry. And so when we analyze this, we look for two things. We look for the shape of the electron geometry and the angles. Nine, we determine the molecular geometry. Mg. Determine the molecular geometry. Um, 10, we determine the polarity. Whether the molecule is polar or non-polar. We're going to analyze the structure, the bonding in the structure, using valence bond theory. No.
Oh, okay. How am I supposed to do it?
That's what we're going to get to, how to do it. This is all of it. Yeah, you don't need to know what it means. You just need to know what it means before the exam, so you have like a time period
Okay, so
to
this is
make
the whole
sure
Bible,
you.
and we're gonna study like one book.
I'm sorry?
So right now we're learning like the whole Bible, but we're only gonna be tested on like one book.
No. This is chapter 10 and 11 combined. And so I'm just going to cover it combined. So rather than just do it one step at a time, which we'll do. For some molecules, we'll do one step. For other molecules, we'll do the whole thing. But it's just going to save some time. I mean, it happens, it happens like you go to scientific conferences. I go to scientific conferences and you listen, they just talk in all kinds of jargon. And it depends on what their specialty is. And most of the time you're just like writing, and then afterwards, for every like 1 hour of scientific presentation, you have to go home and you spend hours trying to decipher, everything. Because if you're new, especially if you're new to the field, it takes a lot of time to go through that type of stuff. But we'll be going through examples of this, so hopefully it'll click by the time the exam comes in 2 weeks. But rather than hit you like the day before the exam, okay, we're going to analyze these structures for valence bond theory. Okay, and then you go, valence bond theory right before the test. It's too much, and it's overwhelming. And so I'd rather hit it early, more frequently, thinking that might be better. And so this is one of the things I was thinking of doing. I mean, because I know, like fewer questions for sure on the next test, and maybe more time for examples. And so that's what I want to talk about. Analyze the structure. So usually we just pick one of the structures to analyze using VB theory. VB theory is called valence bond theory. Valence bond theory is the light version. And so I like to call this quantum mechanics light. Quantum mechanics light. So this is like the diet version of Coke, or this would be the light beer version of the beer. Versus the full version. The full version of quantum mechanics is called molecular orbital theory. Molecular orbital theory is a bit more difficult to analyze. We can only do the very simplest molecules. The only molecules that we're going to analyze using molecular orbital theory are diatomic, 2-atom molecules. 2-atom molecules, they're get kind of boring quite quickly. Whereas we can analyze very complex molecules with valence bond theory. We can analyze proteins, we can analyze big molecules using valence bond because it's so simple. And so molecular orbital theory is much more powerful, but this is the quantum mechanical full version. And it's much easier to do calculations with molecular orbital theory. Actually, if you have a quantum mechanics program, like Spartan or something like that, this is not hard to do, but you don't actually do it. This we can do with pencil and paper, so straightforward valence bond theory. They just differ in the way that they describe bonds. In valence bond theory, a bond is described as overlap of atomic orbitals. However, in MO theory, a bond is a bit more complex. A bond in MO theory is described as LCAO to form new orbitals called molecular orbitals, MOs. And so LCAO stands for linear combination of atomic orbitals. Linear combination of atomic orbitals. And so what we do is we take atomic orbitals. We have two types of atomic orbitals that we deal with in this chapter. They're the atomic orbitals that we dealt with in chapter 8. And so when we look at AOs, atomic orbitals, they're familiar ones, like these. These are called unhybridized AOs. The S atomic orbital, which is a sphere, the P, which is like a dumbbell, the D, which is like a clover leaf, the F, which is like multiple leaves, etc. But in this chapter, we're going to be introduced to a new set of atomic orbitals called the hybridized atomic orbitals. The hybridized atomic orbitals are going to be combinations. So for example, if we take an S and a P and hybridize those together, we form an sp orbital. An sp orbital takes one part of S and one part of P and mixes those together. And we get an orbital that kind of looks like a mix between S and P. And so this is called a hybrid orbital. This is similar to what we do when we try to generate the resonance hybrid from resonance forms. We have SP, we have SP2, which is one part S, two parts P. We have SP3, we have SP3D, SP3D2. These are the 1, 2, 3, 4, 5 different hybridized atomic orbitals. There are more, but these are the 5 main ones that we look at. So if we take these atomic orbitals here and then do this quantum mechanical procedure of linear combination of these atomic orbitals, then we generate new molecular orbitals. The new molecular orbitals have a different scheme over here. The MOs we recognize by sigma. We have something called a sigma 1s. This is the simplest. Then we have a sigma star 1s. And the sigma 2s. This is the Greek letter sigma, and the sigma star 2s. And then we have sigma 2p's, sigma star 2p, pi 2p, etc. And then we can do the hybridized orbitals as well. So we could have a sigma sp3 that. Etc. And so we learn about these MOs, but we're only going to do the very simplest MOs. So there aren't that many. And students just usually memorize them, the MO diagram. The AO diagram, have you already memorized the AO diagram? No?
Like what? No.
Atomic orbital diagram?
Oh wait, that one? Yes. I just didn't know what you were
1s,
referring to. Wait, I thought-
2s.
Yes, I know that one.
2p.
I know.
I'm trying to get you, trying to throw out more jargon your way so that you could recognize the connection. AO is just atomic orbitals, and atomic orbitals are S, P, D, F. So you can make the connection there.
Oh, it's going to be because electron? Maybe?
I'm sorry?
Why is the order what it is? Why is it S, P, D, F, G, H, and then it follows the alphabet, but it starts with S, P, D.
SPD comes from spectroscopy.
Oh, shoot.
They didn't know this stuff. They didn't know this, but they could measure the spectrum of it. When they measure the spectrum, they come up with sharp, principal, diffuse. And then finally, when they came up with a theory, they were able to connect the spectrum with the theory. And so that's what happened.
Okay.
So chapter 10, I think, starts with valence bond. So I kind of wanted to talk about valence bond right now. So when you look at chapter 10, it starts with why bond. Not everything bonds. You know what doesn't form bonds? Everything forms bonds, pretty much on the periodic table, except for what species? Noble gases. The only species on the periodic table that do not form bonds are the noble gases, but everything else forms bonds. And why do they form bonds?
Because they're not stable.
Yeah, right. They're not stable. They're more stable if they form bonds. And so why bond stability? Of course, except for the noble gases. The noble gases become more unstable if they form bonds. They become less happy. And so let's write that exception here, except noble gases. So we'll take the simplest atom. What's the simplest atom on the periodic table? Hydrogen. And hydrogen has one electron in the what orbital? 1s orbital here. And there are different ways we can represent that. We can represent that with 95% probability boundary and an arrow. We can represent that using these. What are these dots called? Somebody was asking me what these dots are called. Today, somebody asked me what those dots are called.
Electron cloud.
Electron cloud. And then they asked me, what do the dots represent?
Possible places where it could be.
Yeah, possible places. And then the density of dots represents what?
The likelihood of it being.
Yeah, likelihood of probability. So we take two hydrogen atoms separated by a large distance. That's fine. If we have two hydrogen atoms separated by a large distance, so we have a hydrogen over here, a hydrogen over here. We have this 1s. This would be the energy level, atomic orbital, energy level diagram. There are lots of different names for this diagram here. The proper name for this would be the atomic orbital, because these are atomic orbitals, energy level diagram. But a lot of people just call it the orbital energy level diagram. And so people memorize this. And then unfortunately you have another diagram, which is the molecular orbital energy level diagram, which has a different pattern to this. And then you have this hybridized orbital energy level diagram, which is a different pattern than this. So, different paint. But the easiest way for memorization, I think, is repetition. So the sooner you see this, the more times maybe you'll see this before the test, hopefully. And then maybe it makes it easier. So what we're going to do is we're going to take these two hydrogens, which are separated by a very large distance, and it's going to have some energy here. There's going to be some internal energy for this and some internal energy for that. And they're going to be separated by a very large distance. As we bring them closer together, what's going to happen is they get closer and closer, the energy goes down until it hits a minimum. This is what we call a potential well, a minimum in the potential well. And the minimum in the potential well is they're going to get in some kind of distance where their atomic orbitals actually overlap, like this. And so we have overlapping atomic orbitals. And that's what we call a bond, overlapping atomic orbitals. And we call it a bond because when we have overlapping atomic orbitals, then the electron clouds also overlap. And if the electron clouds overlap over here, do you know what we're going to have? We're going to have twice as many dots. We're going to have twice as many dots in what we call the internuclear region. The internuclear region, typically what we do is we draw an axis along the nuclei here. So that's the internuclear axis. And if we look along the internuclear axis, we have overlap of atomic orbitals within the internuclear axis here. And that creates a bond. How does that bond hold the atoms together. How that bond holds the atoms together is electron cloud is what charge? Negative. And the nucleus is what charge? Positive. And so what we have is we have negative positive attraction. So the two nuclei are going to be attracted to this higher density region of electron cloud here. Do you see that? So they're going to be pulled towards the electron cloud. And they're going to reach a distance where the attractions are optimized, because if they get too close, what happens if they get too close is the two nuclei begin to repel. And so if you try to force the atoms closer together, then we end up going out of the potential energy well. This is energy on the y-axis here. And if you try to force the atoms even closer together, then the two nuclei get too close to one another. And when the two nuclei get too close to one another, they begin to repel. And that destabilizes the molecule. And so there's an optimum distance here. This is called the bond distance. And that would be here at the bottom of the potential well. And so why do the two hydrogens bond? Because of this stability, bond distance. Here. This is minimum energy. Another way of thinking of this is an exothermic process. So when we form a bond, it's exothermic. In order to break a bond, is that exothermic or endothermic? Like, say I want to break a bond. Does it cost energy to break a bond, or does that release energy to break a bond? It seems to cost energy both ways. But, when we're looking at these electrical attractions, in order to break apart the two hydrogens, is that going to cost you energy? Yes. In order to break apart these two hydrogens, it's going to cost me energy here. And according to the first law of thermodynamics, the reverse process should release the exact same amount of energy. And so when we do bond formation, it's exothermic, stability. When we do bond breakage, it's endothermic. We're going up in energy. So here we're going downhill in energy. So this is valence bond theory. And so we're analyzing hydrogen using valence bond theory right now. So the other thing we would do for valence bond theory is look at the AO energy level diagram, the atomic orbital energy level diagram. So let's go ahead and do that. So this is H2. There are different ways I could show the H2. I have one arrow here for one electron, and I have to flip the other. And so if this was spin up, it can't stay spin up, because both of these cannot be spin up. One has to go spin down. So I'll do the right-hand hydrogen spin down. That's because Pauli exclusion principle holds here, even though we have two orbitals here. How do I deal with the two orbitals? How I deal with the two orbitals is like this. Let's take the left-hand hydrogen. I have a 1s orbital here, and I have the spin-up electron here. Then we go over to the right-hand hydrogen, and I have a 1s orbital here, and I flip that one spin down. And so what's happening here is we're having a sharing of electrons. So what happens is the spin down electron is not localized in this orbital here, but it's also shared over here. So maybe what I'm going to do is I'll just color code this one red here. So that's the spin down. And so what we have here is this spin down one completes the duet for this hydrogen over here. And so this is how we kind of count things here. So now the first shell on this hydrogen atom is filled. The first shell just consists of 1s orbital. That's the first shell on the left-hand hydrogen. If we look on the right-hand hydrogen, what's happening here is this black electron here is going to be shared over here. So what we do with duets and octets is we double count, because we have this sharing of electrons. And so now both hydrogens have a duet. They just so happen to be sharing the same electrons. Do you see that here? And so we double count when counting octets and duets. Did I talk about, I don't think I talked about formal charge, did I? No. Well, when we count duets and octets, there are other ways of counting electrons. I forgot to do this. These are some additional rules for Lewis structures. Okay, number one for Lewis structures, determining the best Lewis structure. In order of importance. The best ones obey octet duet rule. And so the number one thing we look for in feasible Lewis structure is, does it obey the octet duet rule? If so, then that's a good structure. So hydrogen does, you know. Normally we don't show two dots like that. Normally we just show a line. And so we double count it. Yeah, duet, duet. That's good. The next thing we look at is formal charge. We try to, the best ones, minimize formal charge. And so, did I tell you formal charge, we make what assumption? 100% covalent. And so let's take a look at hydrogen. Like this. We could show either as two dots or one line. Formal charge, 100% covalent means it's 50-50 splitting of the electrons. So if we do that, we have two electrons. One electron goes to the left, one electron goes to the right. And then when we calculate the formal charge is equal to the normal valence or the normal number of valence electrons minus the number of electrons atom possesses or has, I'll just say has, in the structure. So what's the normal number of valence electrons for hydrogen? 1. And how many electrons does hydrogen have in this structure? 1. And so we have 1 minus 1. So it broke even. So it gave 1 electron and got back 1 electron. So its formal charge is 0. We normally circle those. And this one's the same. It would be 0. Note over here, the sum of the formal charges is equal to the net charge. So if we add up the two formal charges, 0 plus 0, we get the net charge of the hydrogen molecule, which is also 0. These are the two most important things in Lewis structures. To determine the Lewis structures. To determine things like redox properties, somebody was asking me, if something's not on the redox chart, what would you look at? Sometimes we don't really look so much at the octet, duet, or the formal charge. You know what we look at mostly? We look at oxidation state. And as I mentioned before, they're not necessarily related, the oxidation state and the formal charge. And it's like apples and oranges. And so if we're looking at oranges, we don't want to be looking at the apples. We want to go to the oranges. But I'm going to talk about oxidation state, although, we don't necessarily do oxidation states here. We can. So sometimes we determine the oxidation state because if we're interested in the properties of the particular molecule, that can lead to additional information. And so the formal charge assumes 100% covalent bonds. That's what we did here. Assume 100% covalent. Oxidation state assumes the opposite, which is what? 100% ionic bond. In 100% ionic bonds, the winner takes all. Now, who is the winner? The winner is going to be the more electronegative atom. Takes all. So hydrogen versus hydrogen, is the left hydrogen the winner or the right hydrogen the winner? Which hydrogen is the winner? Well, it's a tie. And so what that means is if it's a tie, then one electron goes to this hydrogen, one electron goes to that hydrogen. Because hydrogen has electronegativity 2.1 on the Pauling scale. And so it's 2.1 versus 2.1. But the oxidation state is equal to the number the normal number of valence electrons minus the number of electrons in structure. So in this case, hydrogen normally has one electron, and how many did it end up with in the structure? One. So the oxidation state is 0. So even though the oxidation state and the formal charge are the same, they mean different things. An oxidation state of 0 is not the same as a formal charge of 0. It doesn't have the same meaning. And therefore, I don't show them the same way. So normally with formal charge, I like to circle these because that's usually what's done. People circle them. With oxidation state, I like to put these in parentheses. And so I would put 0, say, in parentheses. Both of these have 0 oxidation state. But when we combine formal charge and oxidation state, we get something usually closer to the true picture. In this case, we don't because it's just 100% covalent. But if something's, let's say, polar, then what we do is we determine polarity. polarity is between the apples and the oranges, somewhere in between. Sometimes it's closer to an orange, sometimes it's closer to an apple. It'd be a hybrid of the two. That's difficult to do because we need some quantum mechanics to do it. And so what we do is we do it very simple. We just look at delta En. And then we don't actually generate the actual charges. We generate the partial charges, delta plus and delta minus. So we'll see examples of this. These are for the bonds. And then molecular polarity. Next. These are the 4 ways of counting electrons. The 4 ways of counting electrons are octet, duet, formal charge, oxidation state, and partial charge. Our polarity. Full charge is very polar. When you have ionic bonds, this is the most polar you can get. I talked too long, actually. Because we go till when? 4? 4. We don't have enough time for the quiz then.
What? No.
There is enough time. You could do it.
I'm kidding.
If you're prepared today and you don't want to, you want to get it over with, you can do it. But you'll be a little bit rushed.
Dang, man, guess we can't take it today. Might as well do it on Monday.
You want to do it on Monday? Antonio, are you okay with that then?
That's fine.
All right, we'll do it on Monday.
If Antonio wasn't okay with it, we take it now.
I was I'm just further behind.
Could I stay like 5 to 10 minutes late if I took it today?
I'm sorry?
If I took it today, could I stay like 5 to 10 minutes late?
Yeah.
What do you say?
He said
He
yes.
said, yeah.
Oh.
Yeah,
You
we
take
said
it?
no, man. You can't take it.
Depends on how well prepared. It could be very quick, or it could take a long time. Well, let's try this one as an example. This is called nitrous oxide, or dinitrogen. Monoxide, or laughing gas. The first thing we could do is we could sum up the electrons. We have 2 nitrogens. How many valence electrons does nitrogen have? 2 times 5. So that's going to give us 10 electrons. And then 1 oxygen, which is 6 valence electrons, and no charge. So we don't have to adjust for charge. So it's going to be a total of 16 electrons. Sometimes, these are just steps. Sometimes we'll skip steps. If you know some shortcut tricks, you can skip steps. Sometimes it's not good to skip steps because if you don't know certain nuances with formal charge, then it's lead to trouble. And so we can come up with 2 different skeletons for this. Maybe an NNO or an NON. Which skeleton do you like? The NNO or the NON? NON? Yeah, NON looks good because NON looks like water, doesn't it? HOH. What would make you inclined to go NNO versus NON? A rule. And the rule is, what was that rule? The least electronegative element goes in the center. But, we see oxygen. Oxygen is an exception to the rule. There can be exceptions to the rule. So let's go with NON and then come up with our structure. So going with NON, the next step, this is not a double-headed arrow. We only show double-headed arrows if they're showing 2 what we call equivalent resonance forms. And so when we go to N, we complete the octet to the most electronegative atom first, which would be oxygen or nitrogen. Oxygen should get the electrons first. It's more electronegative. And to complete the octet, I need 2 lone pairs. That gives me 2, 4, 6, 8 total surrounding it. You know. And then I have 8 electrons left over. So I'll give 4 electrons to each nitrogen. 1, 2, 3, 4. And that gives me 8. And so I have 2, 4, 6, 8, 10, 12, 14, 16 electrons. Does that look like a good structure to you? No. What's the problem with this structure?
Nitrogen doesn't have an octet.
Yeah, nitrogen does not have an octet. When I look at nitrogen, it only has 2, 4, 6. Oxygen's good. Oxygen has an octet, 2, 4, 6, 8, and this nitrogen only has 6. And so I should try double or triple bonding.
Double.
Let's try double bonding. When I try double bonding, what I do is I move a lone pair into the bond. And so right now, this lone pair belongs entirely to nitrogen, but if I move it into the bond, then it shares it with oxygen. And when it shares it with oxygen, then one electron belongs to nitrogen, the other belongs to the oxygen. But the question I have is this: should I take a lone pair off the nitrogen, or should I take the lone pair off the oxygen to share? Usually you would take it off the nitrogen because nitrogen is less electronegative, so it'd be easier to take it off. But if we take it off the nitrogen, does that solve our problem? No, because even if I move these into the bond, I still have less than an octet. And so the only way to resolve this is to take it off the oxygen. And so what we're going to do is we're going to take a lone pair off the oxygen and drop it into the bond here and see if that resolves the problem. And so I'll have this. Now I only have 1 lone pair on the oxygen here. But did that fix the octet on nitrogen? Yeah. This oxygen now has an octet. But this, I'm not the oxygen, the nitrogen. The oxygen always had an octet. Even when I made the double bond here, it didn't change it because now it still has an octet here. But the problem is with this nitrogen over here, it still doesn't have an octet. And so I should make another double bond. And what I'm going to do in this double bond is just take this lone pair here and form a bonding pair here. And so that's going to leave the oxygen with no lone pairs. So what we end up with, so this is just a progression here. What we end up with is nitrogen double bond, oxygen double bond, nitrogen. And there are 2 lone pairs on each of the N nitrogens. And now everything has an octet. This nitrogen has an octet, this oxygen has an octet, this nitrogen has an octet. And so the octet rule, the most important rule, has been checked. So are we done? Not quite. What we want to do is look at the next most important factor, and that is we want to minimize the formal charge. And so let's count the formal charges in this. When we count the formal charges, we divide up the electrons differently than the octet. So let's look at counting the formal charges in the final molecule we have generated there. And counting the formal charge, oops, it's like this. What we do is we split the bonding electrons in half. Because formal charge assumes that we have 50-50 sharing. Even though oxygen is more electronegative, it's not going to get extra electron cloud. Half of the electron cloud is going to go to nitrogen, the other half is going to go to oxygen. And then we count. The formal charge on this nitrogen is equal to the normal number of valence. What's the normal number of valence? In other words, nitrogen donated 5 electrons to the structure. how many electrons did it get back?
6.
It got back 2, 4, 6. So 5 minus 6 is minus 1. In other words, it ended up with an extra electron, correct? So this is like, there's talk about the Department of Education, stuff like that. But, there have always been complaints from educators, like in California especially. California sends more tax dollars for education to Washington, but gets less tax dollars back. Have you heard that?
Yeah.
Yeah. But some states come out ahead. Well, nitrogen came out ahead. And so nitrogen donated 5 electrons to the Washington and got back 6. However, what about oxygen? How many did oxygen donate? Oxygen donated 6 electrons, but it got back how many? How many did you get back? 4 electrons. So this is the complaint with California educators. California educators always complaining about donating 6 electrons and only getting 4 electrons back. But anyway, this comes out to 2. And so that means it is too short. In other words, nitrogen came out ahead by 1, so it gets a negative formal charge, and we circle it. And we don't write -1, we just write the negative sign. Oxygen donated 6, but only got back 4, so this comes out +2. And we'll circle that. And this nitrogen over here donated 5 and got back 6, so this one came out ahead 1. And so those would be the formal charges. And then we think about this, does this seem very stable to you? Nitrogen taking 1 electron each from oxygen, and oxygen being short 2 electrons? No, it doesn't seem so stable. And so I'd start worrying about this structure. And so that means I should try this structure next. Maybe this one would give us a better distribution, because the best is to minimize it. When we minimize it, that means you put in 5, you get back 5. And so we break even, 0, 0, 0. Sometimes we can't avoid a charge though. So for ions, we always have to have a charge. But for neutral species, it's nice if we could go all zeros. And so why don't you try this one next, NNO, and tell me what you get. For this particular structure. Try to pause this.